This is the first time I go to a conference and that so many people tell me they are really looking forward to my talk. It remembers me of Albert Cohen, who told me once that, my friend and colleague Albert Cohen, who told me once that the less I speak about my own work in my talks, the more attention I get. Anyway, so this is the second talk for celebrating the 60th birthday of Oleg and Sasha, and of course, this talk will be a little different in style from the one of Philip, with different people, of course, and I'll probably be a little more formal, more Russian maybe in a way, I don't know how to say. So, first of all, I would like to address to Oleg in a proper way, and well, fulfill a very old promise to him. Please, it won't take me more than 30 seconds, so I thank you for your indulgence. Дорогой профессор Lepski, дорогой Олег, я горжусь. Выпавшей мне честью поздравить тебя своим юбилеем. На твоих научных трудах выросло целое поколение статистиков. Ты был примером для всех нас. Я еще долго мог бы поздравлять тебя по-русски, но, наверное, лучше перейти на английский. Спасибо. I'm extremely pleased to give this talk. I thank so much the organizer for giving me. I couldn't think of a greater honor. Well, I could think of one greater honor, but this is the story of Oleg, but this is not really the story of Oleg. This is my story of Oleg, and it's a difficult task because the work of Oleg is considerable. Here you can see the whole collected work of Oleg printed, which I got from LSciNet. And actually, it's a little more because the first paper were in Russian, and I could only retrieve some abstract in Russian. And of course, I had to pick things out of this very thick body of work. So it will be a little personal. It will also follow my own likes and the part I know best. And of course, in this story, which will be a little bit between history and legend, there will be inaccuracies, there will be oversimplification, and there also will be omissions. So I apologize in advance for all this. So the organization of the talk will be completely obvious. I will first give a brief overview of Oleg's career, and then I will divide it into three parts that correspond to the three countries where he spent most of his academic life. It's interesting because those three countries have always shared a mutual fascination from a scientific point of view, from a cultural point of view, and Oleg went through that. Of course, there were also antagonisms between the three countries for the last 2 centuries, but this is way over now. And if I have time, I will say a word of conclusion, but I will have time because I'm never granted 1 hour here in Lumini, so hopefully I will come to my conclusion in time. So the first part will be devoted to the Moscow years, and I will spend a little time about the early works of Oleg. I'm thinking, I was curious to understand better what he was doing as a beginner in mathematics, as a PhD student, what the kind of things he was looking at. Then I'll take some time about his seminal paper about adaptive estimation, or rather no adaptation results that made him famous and somehow let him be known beyond the Moscow circle and worldwide. Then I'll try a little bit to tell you about what became his program. What you see, there's this one line of research in Oleg's work of building a kind of general and universal theory of adaptive estimation. there were a transition part of his life, what I call the Berlin years, where Oleg started to collaborate with many people, and that was a really blossoming part of all ideas. There were extremely nice and interesting results. I will be only able to be very superficial about that time. I will nevertheless indulge myself to talk to you about a little bit about the part of the work we did together about the random normalizing factor, because it also, I think, has a link toward the adaptive confidence sets, and we'll say a little bit about that. The third part is about the Marseille years, and here I picked one topic, anisotropy, which I like very much, because I think it's important also, because I do believe that to some extent it is the study of anisotropy that led progressively Oleg to rethink and somehow reformulate his whole view about adaptive estimation. That led to the recent work, well, recent over the last 5-10 years, that he's been doing with Sasha Goldenschluger. So, first, a brief overview of Oleg's career, and this is Oleg as we know him, as we love him. But what do we really know about Oleg, okay? We know him, of course, as a mathematician, as a statistician, an academic which has had a complicated life like many of his folks through the years after the fall of Soviet Union. And we also know him as a poet, or rather, I guess, political pamphleteer, and a friend. So no worries, this part is postponed to whatever's going to happen after dinner. I still have anecdotes and personal things to tell you about Oleg, but this is for later, okay? It's a teaser for the second part of the talk. No, I will rather insist on the life of the mathematician, the statistician, with a view with this rich and interesting life he had that definitely influenced his science. So when we think of someone between a mathematician and a poet, let us try to look at what Oleg was in his early years. Would he become a poet? Would he become a mathematician? So I have this beautiful picture of him at the age of 18. Okay, and here, I don't know what you think, but I could well see a poet in the making rather than a strong mathematician who will build this thick theory. But nevertheless, at the same age, I also could get this picture. This is the picture of Oleg when he was on his when he was trying to make a little money, if I understand correctly, as a young construction crews. And here, yeah, we can see the builder or the future theory maker coming up. But this builder would work with many people. He would be surrounded with friends and colleagues. And here I see this as a metaphor of all these future co-authors in this crew. I think it was the Pulsar crew. This was taken in 1975. And so he would never be alone. Sometimes he would try to do things in an orderly way. And this is what I get from the second picture of him at the same age. But we see that his troops were probably never, also he seems to be very focused. This is not always the case for the friends around him. But the picture I like best about this period, this is the last of this series that I'm going to show you in a moment, is that, oh no, sorry, it's that one. Here I see, well, a handsome, youthful young boy of the age of 18 with his future beyond him. And I like the previous picture too, because that was taken around 2010, and that's Oleg after all these turmoils, okay? So the builder has finished, he can be satisfied with all this, but you may also want to see the poet, who is still thinking near the ancient ruins of the Mediterranean, well, wherever this is, I don't know, unfortunately. So now, more seriously, let me give you some insights about the career of Oleg, and I'll be very brief. This is just one slide of facts about this. I'll go in more detail throughout the talk. So first, obviously, he was born 60 years ago. His father was an architect. This has a very important impact on him. Whoever has been in foreign cities with him knows that he likes very much to visit buildings. And his father, Vasily, if I'm correct, So now if you want to write to Oleg an email properly, you know that you shall write Oleg Vasilich.
Correction is needed.
Oh, Vitaly, sorry about that. It has to be Oleg, I don't know, Vitaly, no. Vitalich, thank you. He studied mathematics and defended his PhD on November the 12th, 1984, the very same day as Sergei Leonov. They actually had the same supervisor, who was Fedorov. So, but in a way, Fedorov, if I understand correctly, was rather the former supervisor of Oleg. The mentor at that time of Oleg was Sasha Korostelev. He was affiliated to the Institute for System Analysis, but still, nevertheless, he would participate to the famous Khasminsky seminar in IITP, the Institute of Information Transmission Problems, where he would meet, where here in this very room, we still have a lot of former participants of this prestigious seminar. The seminar was led by Khasminsky, but there were senior professors like Pinsker and Professor Ibragimov who would, this is the way I imagine, I'm telling you this is my story, this is not the true story, that would come over from time to time, coming from St. Petersburg, Leningrad at that time. And after the end of Soviet Union, Oleg, there were difficult times I'll briefly allude to later. In 1992, he made his first trip to Western Europe in a postdoc in Louvain-la-Neuve. And then he was appointed, he got a position in the Humboldt Universität, between 93 and 98, but it stayed all the time in the VIAS, actually in Volodya's office. And then in 1908, he got this professorship in LATP in Marseille, up to now. Highlight of his career was his medallion lecture in 2005 at the GSMF conference in Minneapolis. Now about some technical he had several PhD students. Some of them, I saw that Nicola is in the room, and many co-authors. This is the official list you get from MathSciNet of Oleg's co-authors. And he records, this is what MathSciNet tells us, 46 published papers between 1983 and 2017. So, I was distractedly listening to Axel Munk's talk on Monday, thinking about preparing this talk, and Axel said something about data, showing data or not showing data, and then I thought that I want to show some data for once from Oleg's work. So what kind of data could I find? Actually, there are some in the paper, but not so many. So I wonder if, well, I just wanted to do a set of things, and I thought maybe this is the data I want to extract something from. And I did the following silly applied statistics stuff. I recorded in the x-axis the papers from 1 to 46, and in the y-axis the number of pages per paper. Why not? And I kind of try to think that maybe there's some kind of increase or something, I don't know. But, you know, it doesn't mean that, this is what we tell to our students, it doesn't mean anything, it's paper by paper. I should maybe project this onto a calendar time, you know, I know stochastic processes, so, and see what it gives if you do it by year. Then you get this picture, which is also not very informative, and then I realized that, yeah, because the papers are published not with delay, there's the backlog, and not always in the order you did the work, and then I realized that noisy data, you can smooth them. So I did the following. I smoothed them using local polynomial for Sasha, and some kind of crazy oracle bandwidth, which I'm not even going to describe. And this is what and of course I cheated a little bit, because this is applied statistics, and I got the following. This is reproducible research. You've got everything here, and you get the data from MathSciNet. So I'm not, except from the support part, which, well, I played a little bit. Don't we do that? Oh, no, you never do that? Good. We got this. And here, I see this picture. I like it because it looks nice, and I just want, and it gives us two. I'm going to use it for two things. The first is that you see, Oleg, in this nowadays life, today, academia is organized about all those metrics, bibliometric and so forth. Whenever you apply for some grant or something, you can show how your production is increasing, and that definitely, what is it going to be in 10 years from now? I'm afraid. The second thing is that, no worries, I want to reassure you, I will only be talking about this part of Oleg's work. I leave this untrodden territory for whoever will do this in 10 or 20 years from now. Okay, so now, more seriously, let us go to the first part of the talks, and let us go about the Moscow years, and Oleg around in the 80s. So, the first ever recorded, published paper by Oleg was actually devoted to solving a statistical problem in stochastic processes. This is ominous. Maybe he doesn't even remember himself. And it was published wherever that was. I'm not able. I gave you my best Russian. I can't do anything more in Russian today. Maybe tonight, but now it's over. And he studied actually a problem of linear autoregression with a quite general assumption, and in particular we studied estimation. He was interested in estimating the parameter of theta in this kind of object when they were exploding. It would be limit theory, find in the Gaussian case Cauchy distribution, and well, this was the kind of thing he actually first studied when he was barely a PhD student. He still worked on that with Fedorov, or at least Fedorov is in the paper, and there was Korolev too, by analyzing time series generated by stochastic differential equations. So he actually did some work on stochastic processes, on statistics of random processes, also, although he always denies it whenever we talk about that. But after probably around 84, 85, he leaves, presently forever, the subject, and moves towards Minimax estimation. At first, it's parametric estimation, and he writes a series of papers. One is with his mentor, Sasha Korolev, about asymptotically Minimax estimation under some series of constraints over the loss function. In particular, this first paper, which I got for a translation, has an interesting introduction, I believe. He explicitly writes there that he studies a situation in which, apart from the natural requirement that an estimate is close to a parameter, the estimator is also subject to additional prescribed properties. This is exactly what Marc will call later, a few years later, constrained estimation. It's interesting because there was no competition between Marc and Oleg because they didn't know each other, they didn't know their work, but they were working on similar things, and well, maybe I'm overinterpreting, oversimplifying. You know, I told you, this is how this talk will be, but I do want to think that maybe he was kind of preparing something without even noticing at that time. I also want to state that he cites a paper by Anbar from Annals of Statistics in '77, which tells us that he was well aware I mean, information was circulating. Maybe people were not circulating, but there were, at least from West. I'm not sure, people who could read Russian maybe would have papers in the West, but there was some interaction, of course. So in particular, in his problem, he'll be able to characterize the minimax rate of convergence and more for specific loss function that technically will, for instance, for this kind of instance, will give you this kind of minimax risk. Yeah, so you see this is something like approximating the function, but under some constraints. There's some application with tests and estimation, test estimation. This is really something that will be recurrent in Oleg's work. Combining testing and estimation methods, this is a motto in his work, I believe. So I'll go quickly about that, but there's one thing interesting I find too, is that at that time, so of course the book of Ibrahimov and Kantnitsky was at this as a pinnacle. Everybody was using it in Russia, but in Europe too, and Oleg works somewhere in between LAN and something which is completely minimax, which is completely non-asymptotic in spirit, using properties of estimator which are already concentration. So I think that very soon, at that time, Oleg was not very much interested in limit distribution in weak convergence, but rather in things that could be formulated in a non-asymptotic way. whatever that means. But that's important because as soon as you leave weak convergence, well, you can start to think about handling a bias, and well, you have a lead towards non-parametric estimation in a way. Around 1987, Oleg presents his famous no adaptation result at the Chasminsky seminar. And this result is quite unexpected at that time, and I would like to explain briefly why, not to the specialists, but to those who are not so well acquainted with adaptive estimation. He shows there, for the first time, that there exist reasonable settings, pointwise estimation of a non-parametric function, where you just can't do adaptation the way you would think. It's important because at that time, it was quite a new topic. It was not completely clear to anyone to work on adaptive estimation. I was raised in a generation where the first question you would ask is, can you do adaptive estimation? But it was not so clear. So the formulation of adaptation was unclear. And what did Oleg? He just simply started by proving that sometimes you just can't do what you think you do. But what is interesting in this paper is that it's a little bit like a child that plays with a toy and that breaks the toy and that readily want to fix it. What did I do? So in the same paper, he proposed a notion of weaker adaptation, so that not everything is lost, that you can actually build something. And he used this construction, which is really something that the first trace we have of what will be later coined Lepski's method. And we have this completely unexpected result. So let me show you the first page of the paper in Russian as it appears, a problem of adaptive estimation Gaussian white noise. And here you see everything. You see Oleg's style, which is, well, apart from the Russian to English, everything is written in the form we are used to read it. Gaussian white noise, minimax risk, etc., and so on and so on. I also want to show you the last page of this paper. It's a beautiful paper. It's 12-page papers. Everything is in it. Just to show you two things. First, that definitely Oleg didn't read much, or at least he was working by himself. But he was well behaved because he only cited 3 papers, but that was Ibragimov, Chasminsky, and Pinsker, the 3 senior professors of the Chasminsky seminar. So he knew that he shouldn't do too crazy things at that time. The other thing I would like, the completely anecdotal thing which I would like to show you is the date at which the paper was submitted. I will just zoom it. The 21st of December, 1987. So, today, actually, we are celebrating the very 30th birthday, day to day, of the official submission of Oleg's paper on the adaptation results. I'm surprised that Arnak, Richard, and Christophe managed to organize things so perfectly, since they're not German, right? Okay, just, you know. Now, what is in this paper? Let me go just briefly into what is in the paper, but let me show you a little bit of mathematics. We're in the Gaussian white noise, and it's much general, the paper, but I'm just to give you the flavor, I'll prove the following important result, that if you take 2 Hölder classes with 2 different smoothness parameters, then you have this minimax lower bound, and this minimax lower bound tells you, of course, the minimax rate for a given Hölder class is that one without the log, but you have to pay this log. This is unavoidable. And then he explicitly builds a sudden estimator, which over finite bounded subsets of the regularity achieves this rate. And the construction is extremely simple. He explicitly writes it for 2 points, just for he explicitly writes everything. This is in his paper. You should have a look at it. And you find already the comparison scheme that will make the progress and success of adaptation over the next year. Okay, I write it in modern form. Here you have the kernel with the target bandwidth, and I forget about the constants. You will allow me, because there are many constants in that paper. I like that. I'm not sure he was so much interested in constants, but I think it's just something. It was the style of the writing. You had to explicitly compute all the constants. So he also looks further, tried to introduce the notion of optimal adaptation in this context, and this is interesting because it introduces the notion of normalizing factor, the family of normalizing factor, which are admissible if so that's when you can't do adaptation. What should you do? You can do something, you can put log, but to what extent is it a good thing? And so he introduced the following notion. He thinks in terms of a whole family of normalizing factors indexed by the smoothness parameter, which he calls which is called the nuisance parameter, and he tries to compare these families. Introduce for that the characteristics here in terms of the subnorm, and just say that you will be a family of factors will be optimal in this sense, if it is admissible, in the sense that you can build adaptation with this specific normalization, and well, you can't improve on it in the sense of the characteristic which he defines. Okay, and this is something that will be also used later for the random normalizing factors, and which has some connections to adaptive confidence sets. So I'm almost done with that part. Just two new features that I find interesting is that what was the state of the art of adaptive estimation at that time? There were very few results, rigorous mathematical results about adaptive estimation at that time. I know there was Efroimovich-Pinsker in '84 and Golubev in '87, but they were all focused on L2 estimation, block penalization, and what Oleg did to that extent was relatively different. And so the interest is that the scheme is extremely flexible, in the sense that here, in this construction, you have the pointwise, but you could think of many loss functions. And this is probably here that you gain in generality from this approach. The other thing is that it's absolutely clear that from now on, the adaptation in the way Alex think it will be linked to a family of given estimator. You start with a family of estimator which are parameterized by some bandwidth, and you try to work that way. So this is the beginning of a vast program of theory of adaptive estimation, which I believe is still ongoing. And what about adaptation in the West? Well, of course, I'm not an historian, so I know that several papers were interested in understanding what was going on. For instance, there was the paper by Stone on non-parametric estimation with random design, where Minimax estimation were established, where Stone explicitly asks for some adaptation, but he has no result. And then, for instance, quite interesting paper, very interesting paper, is a paper by Herdle and Maron in '85, I think, where they claim that they solved the problem. There are many insights in this paper, but the proof probably doesn't qualify for what we would call today a rigorous proof of adaptation. They work the other way. They had procedures, of course, cross-validation was known, Akaike was known, and they tried to understand in which way they can build correctly with their procedure, whether Oleg was more from the abstract point of view. So the two are complementary in a way. So at that time, by that time, he subsequently produced 3 papers that develops his view on kind of the start of a general program of adaptive estimation. These are difficult paper. They are interesting, very interesting. You can read them, but they are they are deep. And here you really go on this vast program of a theory of adaptive estimation, where he tries to systematically answer several questions. Finding sufficient condition, what you do when you can, when you cannot estimate in several situations. I just have one slight criticism about is that probably Oleg put all his energy on the math, and then he came short of inspiration for the titles. Because if you look at the titles, maybe this is due to translation, they all look alike. Yeah? And sometimes they look strange. Look at asymptotically adaptive estimation, scheme without optimal adaptation, adaptive estimates. Clearly he's obsessed by the topic. This is what you can read from the subject. But it's hard to get more from the title, except that it will be about adaptive estimation. But as I told you, I'm not going further into that direction because this talk is not a discourse on method, so let us move on. And the next slide is specifically for my friend Richard Nicoll, because he was the first one to take the bait and tell me, as soon as I arrived in Lumini, haha, you're going to talk about Descartes and le discours de la méthode. I didn't really have thought about it. It was just a practical joke I was thinking when preparing my abstract. So I show you one of the first edition of René Descartes' Discours de la méthode. It's interesting because so there's other scientists who were having their method. And it's interesting because the subtitle is Pour bien conduire sa raison et chercher la vérité dans les sciences. To conduct correctly one's reason and find truth in science. So this is this I like, and also this is for Sarah because it's in Leiden. And why is it in Leiden? Because Descartes had to, he published this anonymously because Discours de la méthode, Cogito ergo sum, that was departing a little bit from religion. And France was not a very liberal country at that time. So he thought it would be, in a way, slightly more reasonable to publish it anonymously in the more liberal Netherlands at that time. So you see, Oleg, there were other scientists with a method who had a difficult academic life. Now I'm going to the second part, the Berlin years. Here you see the picture of the Weierstrass Institute. And now, uncertain times followed from after the collapse of Soviet Union. For all the participants of the now former Helsinki seminar when he left Russia, and it was a difficult time for everybody, every scientist there. So Russian people is a resilient people. They've gone through very harder time over the 20th century. But nevertheless, if you think of the careers my generation has had, life was way easier. So in a sense, thanks to Sasha, Oleg, after some times where he basically practically was only taking care of practical life, Sasha managed to have him in Louvain-la-Neuve, where he did some kind of postdoc stay, and where he gave his first talk in English. So this is a little anecdote that I want to tell, if it's fine, Oleg. Sasha was extremely skilled in languages, but that was not the case of Oleg, because Oleg never thought that there was much point in learning foreign language when you were in a country where you could not get out. Of course, he could not predict that a few years after. So he gave us talk, but he was not able to produce it in English. So Sasha did it for him, and Oleg did exactly what I've done for you for his first talk. And I can tell you this is hard. He gave a lecture without really understanding what he was saying. Of course, he was talking about his research, but the pronunciation was a terrible ordeal. But anyway, in less than 1 or 2 years after, his English was fluent, he learned French. Well, that was just a difficult time. Another thing is that then in '93 he was invited to Berlin by Michael Nussbaum, who at that time was the head of the statistics research group in the VIAS. Now it's Volodya. And he was affiliated to Humboldt, and as I said, he would stay all his time for a few years, and Volodya was there. And there started this very strong collaboration that lasted for the Berlin time, where they did some tremendous work. I'll show you that in a second. They did a lot of papers, extremely insightful papers, very original papers, where they go on about adaptation, testing, efficiency, adaptive efficiency. In those results, there are some results which are crazy in a sense, because for instance, okay, I don't want to get into details, but for instance, you can't have efficiency for pointwise estimations because somehow the risk doesn't degenerate. But if you do adaptive estimation, because of the inflation, you can do something like that, okay? And so that were completely unexpected results, which they do. In Berlin at that time, there was also this prestigious seminar, which is the VIAS seminar that some of us have gone through, which was headed by Nussbaum. Now it's Volodya and Marcus who Hi, I don't know where's the camera, but he told me that they will look at the talk. And there was also the unavoidable, like Oleg said, Gergerdle at that time. That was Wolfgang Herdler who did a lot to put people together, to give them means to work together. And less than a month ago, there was the celebration of the 50th anniversary of the VIA seminar that was organized by Marcus and Volodya. And here you have a picture of Yuri, Oleg, and Wolfgang thinking of the good times backward. So beside the VIA seminar, there was also at that time the Paris-Berlin seminar that was launched around 94. We were not able with Dominique to remember if it was exactly 94 or 95. It was a yearly seminar that would alternate between Garchy in France and Schmerwitz in former Eastern Germany, if I'm correct. And that was this was a very interesting time. This seminar somehow stopped for some reasons in '98, and in a way, in a sense, was followed by the Lumini we have today. So I take the vanity to think, I want to think that in some sense, you have this transition from the Chasminsky seminar to the Paris-Berlin year, because at that time there was this connection, transition, that was through Lumini. So maybe in a sense we can say that this is the descendant in some sense of the Chasminsky seminar. Let me just say, I'm running out of time already. Let me just say a few words about an astonishing result, a crazy result of that time between with Oleg, Sasha Spokojny, and Nemirovsky. It's about when you want to estimate the norm of a functional. So when you want to estimate the norm of functional in white noise, do you think that that is going to be, well, it's a functional, so you do plugging, you do this kind of things, and it will work. But the problem is notoriously hard, and the results are relatively unexpected. The rate lies somewhere between n to the minus 1/2 and the classical minimax rate of estimation, but it actually depends on the oddity of the exponent r. Okay, you have different rates. Actually, it means that if you think in terms of simple interpolation argument, it will just not work. And what you have is the following result. You have a following result that the minimax are, so there were many results that were known at that time. For L2 it was about quadratic functionals, L infinity, L1, but in LR, in all generality, it's unexpected. If you don't have an even integers, you have this rate of convergence, but if it's an even integer, you can do, you have something else. This is somehow linked to analyticity of t to the power 2, well, anyway. And it was using really tricky, formidable techniques that had been developed formally by Ibrahimov, Nemirovsky, and Chasminsky. About the normalizing factors, well, this is the time where I met Oleg. I finished my PhD, was already working on this, and I kind of made a pre-doc stay in Berlin in VIAS. This is where we met, and this is where I had the opportunity, the privilege to work under his guidance. And that led to our joint paper. And the general principle of random normalizing factor is the following. I just explained it for just two, like as usual, just for two cases. So you take your favorite statistical model. Here, this is reminiscence of a smoothness class, but that could be something completely different. And you have this kind of inclusion structure. Okay, one is included into the other, which you can always make, of course. And you have associate minimax rate of convergence. And you assume that adaptation is possible in that sense. So be careful here. The normalizing factor, adaptation, is written in terms of the function itself. It's completely equivalent to what you think, but it means that uniformly, honestly, you would say, Richard, you replace the normalizing factor by what it should be, the correct rate when you are in that space, and the other when you are in the complement of that space, and you know that you can build an adaptive estimator. But of course, when you do that, from this result, you can say, with overwhelming probability, which depends on the constants which you can tune, that your function will be in a ball of center the estimator and radius this normalizing factor. But the normalizing factor depends on f itself, so it's not a confident statement. So Oleg asks the following: can you replace this Rn of f by something random, data dependent? And he asked this question back even in 96, because he gave his first lecture in Garchid in 96. And here, this program is to replace RNF by something which is random, and that satisfies certain things. First, it has to converge over sigma min when you replace it, so that what we would call honesty today. Adaptation is still in force. It's important that you, he will not negotiate. It has to be adaptive all the time. And if you are right, if you are in the very smooth class with overwhelming probability which you can control, you will actually improve what he calls accuracy of estimation. You will do better than the worst case that you would get from the minimax rate of convergence over the whole class. And now the question is that, can this random normalizing factor be actually of the same order of the minimax rate over the smooth class? And the answer stays, for instance, for smoothness, in elder smoothness in Gaussian white noise, you have the following result. It tells you the following, that, well, first of all, when you are not smooth, you get what you expect, but when you are smooth, which of course you don't know, you will see this. This is something that will appear from a certain testing procedure, and you will get something which could be what you want or not. But if it is not, it will be the L2 testing rate. I forgot to mention that here in this approach, it's crucial that you work in L2 norm for the loss. So in a sense, for instance, when beta max is between beta min and 2 beta min, you have that this will be the right order, and or the worst order if you want, and you will be fully adaptive. So you will get a full adaptive confidence ball in L2. Otherwise, it's not too bad. You will still get something. You will, if you don't have this condition, you will still have something. And there's a theory of optimal random normalizing factor that show that in the sense defined by Oleg, this is still optimal. Okay? Now let me move to the third part of my talk, the Marseille years. And this picture is for Dominique. The other night at dinner, we had a little disagreement, as usual. And we were discussing, do you prefer mountains or do you prefer the sea? And of course, I had prepared a picture of mountain, of the Calanque, which looks very nice. And Dominique said, no, the sea is more welcoming, because when you have the sea, you have harbors. And harbors are more welcoming, and I prefer the notion of harbors, because you can go there. And I thought she had a point, as always. I put this picture as a metaphor of the city of Marseille that welcomes Oleg after his odyssey through Europe. Now, moving to France was not completely trivial. Technically, in the mid-90s, in part thanks to the Paris-Berlin seminar, Oleg was well known here, and there was an active supporting group led and driven by Dominique, Gérard, and Sacha that prepares the next move to Oleg, and that will be France. So, well, we know very well all the characters, they're in the same room, but there's one person I would like to acknowledge here, who is Etienne Pardou, at that time the head of the LATP, who did a lot who did what was to be done in order that Oleg could be attracted to Marseille. I have an anecdote for that, but this is for tonight. This is the third part of Oleg's career, and here you see the support crew of Oleg, Dominique, Gérard, Sacha, who are here, and also Etienne Pardou. This is what I believe is what has become the pulsar crew of the 18 boys and girls that were working with Oleg in the picture we saw before. Now moving to France, then soon Yuri Golubev would join Oleg, and as a researcher in CNRS, and the two would build practically out of nothing a school of mathematical statistics in Marseille. This group will be alimented in part by students of Dominique and Sacha. There will be Laurent, Christophe, Florent, Thomas, and starting in 2000, now we are coming to today's years, it will organize this yearly mathematical statistics conference that we know as today, the Lumini conference. Here you have this picture of the Marseille school, Yuri, Laurent, Christophe, Florent, Thibault, and Thomas, Thomas, Thibault, and many others of their PhD students who moved to other institutions, Clément Marteau, Sébastien Lousteau. I'm forgetting people, but a whole community. And of course Oleg. That is taken in 2002 in Marseille. So at that time, you see, he's achieved a state of steadiness as usual, but he looks happy actually. Now about mathematics. So I want to talk a little bit about anisotropy, okay? Because that was a subject that was undertaken by Oleg during those years with Dominique and Gérard. So I just got a picture with Oleg and Dominique. So for my story, I will just pretend that Gérard is taking the picture. So we have the three of them. And the problem is the following. It's a relative, you are in Gaussian white noise as usual. Now you are more in a Western style. It's not epsilon anymore. It's n to the minus 1/2. This is now how people will write, but it's of course exactly the same. And you want to estimate the function f in LP norm for all LP norm, adaptively if you can, optimally if you can, when the smoothness of f is non-homogeneous. So let me just recall what is the situation in the homogeneous case. Okay, that goes back to the works of contribution of Donohoe, Yen, Dominique, and Gérard in the 90s by means of Bezier space and wavelets, where they shaped the whole situation. And you can get, at least in the isotropic case, you can get a pretty simple picture of what's happening for the minimax rate of convergence. So here you have only, it's in isotropic case, you have only one regularity, S1, and you measure it in one norm, LP1, okay? So I write NP, 1 over P1 here, S1 here, and I represent a smoothness space, a Bezier space, in this plane, okay? So here, for a given S1 and a given P1, I have my space. So what kind of information do I have about other? If this function belongs to that space, it certainly belongs to other Bezier space, but which one? So if I increase the norm in which I measure the smoothness, that way, because I go leftward, then this will be given to me by the Sobolev embeddings. And it will be here this point will be S1 minus D over P1. And if I weaken the way I measure, this is simply the natural embeddings that tell you nothing. You don't lose anything, you don't gain anything, okay? And now if you want to compute a minimax rate of convergence, there's a very simple way. I learned all this from approximation theory because in the group of Dominique and Gérard, this is really what we were doing intensively in the 90s. You take the line which has intercept minus d over 2 and which has slope p d over 2, and p is the loss function in which you will measure it, okay? And this line will intersect this whole set of information you have about your function. Oh, you don't have it because you are working adaptively, but mathematically. And that point will give you a smoothness, which you can read here. So in that case, the smoothness is just S1, okay? And the rate of convergence that we'll get will always be n to the minus S1. Well, so it will give you a certain smoothness, which I call S bar. And the rate of convergence will always be n to the S bar over 2 S bar plus D up, well, possibly up to log terms, and always. And what is interesting is that now, if you strengthen the way you measure the loss, okay, and then your line will move that way. Here it will hit what is called the critical point, the critical case, okay? And here you will get into the sparse case. And for instance, if you are very sparse, in the sense that you are measuring, you have smoothness information in a very weak, in this norm, but you measure smoothness in this norm, which is strong, but with a much stronger loss, then this S bar will degrade. And it will be, well, it will be an explicit formula, which you can compute readily by simple elementary algebra, and which gives the somehow complicated formula, okay? So that's, but it will be of this form. S bar will be either this, we get what we call the dense case, or S bar will be somewhere here, and this is what we call the sparse case, and it will involve everything. It will involve P, it will involve all the parameters. And we have this critical point, which is more subtle. And it all goes, as soon as you have the theory that was developed by Dominique and Gérard about injection of weak space, of strong space into weak space, you get weak space, strong space, sorry, you get everything. So now the goal is to generalize this to the anisotropic case, and it's very, it's absolutely unclear how to do that. So the three of them define this generalized using Nikolsky space and these kinds of machinery. They develop the notion of Bezoff space with homogeneous smoothness in directions, because you are now on the hypercubes, and for the different P, okay? And you get a relatively natural definition for a certain difference operator, which I will not describe. And in this setting, they obtain in two papers, which are really difficult papers, they obtain a complete formulation of what's going on. There are some log terms which are missing in these slides. I mean, they are not for the dense case. They get everything, the minimax rate of estimation. And in the sparse zone, so here you have the sparse and the analogous of those two zones, which are given by this equation. And if you put all the SI and PIs to be equal, you will retrieve the situation as described here. And what happens in the sparse zone is more intricate. I will not give the formula, but it's explicit. So they managed to characterize everything. And what I find interesting is that as far as I understand, as far as I've discussed with some people, but not Oleg, it's really this kind of difficulties that were encountered that somehow made Oleg, because the Lepski scheme in the classical way would not really work. Something else had to be developed, generalized, and somehow this led him to rethink, I believe, him and the other people with him, to rethink adaptation and move to something new. The third adaptation period, the way I call it. But now I want to move from anisotropy to the third adaptation period. And the third adaptation period, you will see this new character, which is Sasha Goldenschlager, who met Oleg in 2000 precisely in this very seminar, conference. Now I call it seminar, the Lumini seminar. And here you have Oleg with Dominique and Sasha, and you have this nice transition from anisotropy over Bezoff spaces towards it. But before that, I want to speak about another fundamental, result of Oleg I like very much. I'll be okay with the time, no worries. Which is a new project where Sasha, Oleg reunite for yet another project. There have been written several papers. I can't tell the whole story, there's too much. And now Anatoly joins the party, and they address something which seems a little weird. I remember the first time I hear it, but which I think is completely essential to the future of anisotropy. Well, this is my prediction for the next 10 years. The result is presented at this famous IMS medallion lecture of Oleg in Minneapolis in 2005. Sorry, and here you have this picture of Sergei, Oleg, and this is Sam Efromovich, where the story took place. The paper is non-parametric estimation of composite functions. So here, what does it mean, composite function? The way I want to explain it is in terms of anisotropy. In a way, it's at that time, thanks to the work of Dominique and Gérard, estimating a function is now fully understood in this homogeneous space. But this is still very dependent on the coordinate of the system. So in particular, if you think of a multivariate function locally as a smooth manifold, a graph manifold, it is a geometric object, right? So depending on the way you choose your coordinates, you might well alter the smoothness whether you are not changing the object itself. So typical examples include smooth image domain boundaries. In a sense, the previous works of Sasha, but other, the curvelets of Dono and Candes in the early 2000s, in a sense, were addressing this kind of problem. and also certain solution of nonlinear PDEs that, with very smooth coefficient, will develop singularities in times. And I think this becomes important at the era where we start to work with statistics and PDE, isn't it, Richard? This is our next project. And if you don't know this paper, I recommend it. It's very illuminating. It's a paper by Devor and collaborator about anisotropic smooth space via level sets. It rethinks the whole story. So for instance, you know, I was intending to talk about this subject here in Lumini, but then Arnak asked me to do something different, so I will just indulge myself one slide of this research program. Another example, which is linked to that, is something I started to tell you about last year in Fréjus. Some of you may remember, otherwise it doesn't matter at all. Well, you have a certain population, age structure population, so there's a certain function which you want to estimate, you observe it in noise, and the function is solution to a certain PDE, okay? It represents the density of a population at time t and age e, which is alimented by fertility b and decimated by mortality mu, okay? And here you have a certain aging process. It could be 1 if age goes that, but it could be any kind of transport. And typically in this kind of topic, you want to estimate G, but the results are, the assumption you made are on mu and B. Okay, so mu and B are in some anisotropic space. G is in some results to be in a certain anisotropic space, but of course, not of course. Of course, for me, having spent 6 months on that with Paulien Jeunesse, who is here on this joint project, you realize that if you change your coordinates, somehow you get along the flow, the inverse flow induced by the transport of solution, then you have another representation, a composite representation that will correspond to a change of coordinates, and G will become F in this new system of coordinates, and F will be smoother. So it turns out that you may benefit from it. And in a sense, this is where lies the interest of one interest of composite function. Another interest is that it encompasses the situation where you have single index and additive models. So I don't want to bother you with formula, but just to show that it's never easy. It's always a little intricate. But in that paper, Sasha, Oleg, and Anatoly, in a sense, characterize everything and the situation where you can benefit from the structure and sometimes you cannot benefit from the structure. This is what they do, and adaptation is done with respect to the local structure of the model, not with respect to the smoothness indices here. Okay, now I'm going to the third adaptation period, but I promised you that I wouldn't go too far into this untrodden territory. This is, in a sense, we have to wait for another 10 or 20 years to think back about this work. There's the Oracle approach, which somehow was triggered, I believe, by the work about anisotropy, where Oleg and Sasha did this impressive body of work about what we call today the Golden Sugar Lepski method. I'm not at all discussing about that. They are here, and they have been giving many talks here, and you were there, almost all of you. But this is what I've just explained to you, put in words. And now comes the end of my talk. So I just need 3 or 4 minutes to try to give a conclusion about this I was about to say this seminar, this talk. I will not translate this. I left it for the Russian-speaking people. But you see, this is the end of my tale, the end of my story, and I feel a little bit like this young man with all these notes trying to say something intelligent, and I feel a little bit on my back, the young Oleg looking at me with benevolent eyes. It's certainly too early. It's way too early to speak of Oleg's legacy. We have to wait for another 20 years for that. I'm ready to do the speech in 20 years. Oh, I shouldn't have promised that. But it's an immense body of work. It includes several people, everybody's here, and we're all in a stat math community. And sometimes we have doubts. Sometimes I have doubts. What does it mean to do all this difficult work in the era of big data, applied statistics, and all of this stuff? But if you look backward, If you look backward of what was the state of the art in the 80s, there were already a lot of applied statistics that were trying somehow to understand adaptive estimation their own way, but they were lacking methodology, they were making inconsistencies, and in a sense there was a missing link. And I do have the vanity, of course it's easy because I'm talking in front of an audience who will certainly agree with me, but I do believe that we don't have to worry because this is a necessary link. It has been proved in the past, and it will certainly be proved again in the future. Now, at a personal level, I would like to make a little personal thing. I had the privilege to work under the guidance of several strong mentors. There was, of course, Dominique and Gérard during my early years. There was Oleg, and there was also Sasha, who supported me all along the way to my career. And I couldn't think of a better occasion to thank them and to express to them, to all four of them, my gratitude for all these years. I'm almost done. I have a small present for Oleg and Sasha, and this is something that you can share, not necessarily evenly, that you might want to find useful for tonight's party, and that will be useful when I'll be telling the other anecdotes. And I thank you very much for your attention.
Merci, Marc.